So if you take, say, 100 independent metronomes,
Right.
right? You set them into completely different tempos and place them on a suspended piece of wood. Well, something impossible happens. Within just a few minutes, without any kind of central mechanism controlling them, they will all perfectly sync up to the exact same beat.
It really is wild to watch.
It's mind-blowing. Welcome to the Deep Dive. Today we're looking at a highly technical encyclopedia entry on something called consensus dynamics. It's a deep intersection of systems theory and graph theory. And our mission for you today is to decode the invisible mathematical rules that govern how independent actors manage to reach a shared decision using only local information.
Right.
Whether those actors are microscopic cells, massive space fleets, or literally just a room full of arguing humans. We live in this world of massive information overload where everything starts with completely different initial values,
Right.
different opinions, different data. So how does anything ever get on the same page?
Well, that metronome example you just gave perfectly visualizes the core puzzle that multi-agent systems researchers call the consensus problem, or sometimes agreement dynamics.
Yeah.
You have this massive group of independent actors, and they're all starting with different initial values, like you said, different tempos or different opinions, maybe different sensor readings.
Oh, total chaos, basically.
Exactly, total chaos. And the challenge is figuring out the underlying mathematics of how they eventually converge on a single reality, a consensus, when there is absolutely no omniscient supervisor or boss telling them what to do. They only have local rules and local information exchange.
Okay, let's unpack this, because before we look at the real-world applications, I want to visualize this mathematical convergence, just stripping away the equations for a second. Let's just look at the behavior. Tell me if this analogy tracks.
Sure, go for it.
Let's say I'm in a massive, crowded banquet hall. Everyone is speaking in completely different volumes. Some are shouting, some are whispering, total chaos.
A nightmare, honestly.
Right. And I want the room to reach a consensus on volume, but there's no guy with a microphone at the front shushing everyone. So my assumption is I just listen to the people immediately next to me, right? And I just mimic the loudest person in my local group. Eventually, the loudest voice just wins out and the whole room matches it. Does that make sense?
I mean, logically, you'd think so. But if everyone actually followed that specific rule, the room wouldn't reach a stable consensus at all.
Wait, really? Why not?
It would just get louder and louder, basically until everyone was screaming at the absolute maximum capacity of their vocal cords. The system would just cap out. It wouldn't converge.
Oh, because everyone is always just matching the loudest guy.
Right. The mathematical models we are looking at describe what's called an unforced dynamical system. The secret here, and unforced is the key word, there's no external force or central commander. And the secret isn't mimicking the extreme. It's actually about a very specific type of mathematical averaging.
So, I'm not just copying the loud guy then?
No, not at all. You are taking the volume of the person on your left and the volume of the person on your right. You calculate the difference between their states and your current state.
Wait,
Then you apply what's called a fractional update.
fractional update.
Yeah, you average them together and adjust your own voice to that exact middle ground. That mathematical fraction, that specific rule of interaction guaranteeing convergence, that's what researchers call the consensus protocol or the agreement protocol.
Wow. Okay, that's actually a really profound physical reality because the math essentially dictates that if a network is going to avoid collapsing or just maxing out like the screaming room, absolute stubbornness just cannot exist. The consensus protocol literally forces a compromise.
Exactly. It mathematically mandates compromise. As long as every single agent continuously applies that fractional update based on their local neighbors, the math completely guarantees the entire network will eventually settle on a single shared value.
The chaos actually becomes consensus.
Right. But, and this is a big but, the final volume that the banquet hall settles on is governed entirely by just two factors:
Okay, what are they?
the initial conditions and the interconnection topology.
Well, I mean, initial conditions seems fairly intuitive. That's just the raw data we start with, right?
Right.
Like if the room is 80% shouters when the doors open, the final average consensus volume is going to be significantly louder than if the room started with 80% whisperers.
Yes, exactly. The starting values sort of dictate the mathematical boundaries of the final agreement. But the interconnection topology is what actually drives the system to that destination.
Interconnection topology.
Yeah, topology is just the formal shape of the network. It's the map of who is actually actively connected to whom.
But how drastically can the shape of the network really change the outcome? Like, if we all end up averaging our volumes anyway, doesn't it all just wash out in the end?
Not at all. Imagine a star topology. You have one highly influential person in the center of the room, and 50 people are only listening to that one person while completely ignoring each other. That central node has a massive, disproportionate gravitational pull on the final consensus.
Oh, I see. Because everyone is reacting to them, but not to each other.
Right. Now compare that to a ring topology,
Yeah.
where everyone is standing in a giant circle. You're only listening to the one person on your left and the one person on your right.
Okay, yeah. Yeah, it's totally different.
In that setup, the information moves much slower around the ring, and the final average will be a much truer reflection of the entire room's initial conditions, rather than being instantly skewed by a single, highly connected hub.
So the literal shape of the communication dictates the reality the group ends up living in.
That's a great way to put it, yeah.
Here's where it gets really interesting, because if this localized math works perfectly in a theoretical banquet hall, I want to look at the real-world applications mentioned in the source material, because the sheer scale of this is staggering. The text actually starts at the microscopic level, specifically calling out physiological systems and gene regulatory networks.
Yeah, it's fascinating. Think about cells. Cells do not have a central nervous system calling the shots for every individual molecule at every single millisecond.
Right.
Yet a gene regulatory network has to somehow reach a biological consensus to, say, differentiate into the right type of tissue or to respond to a pathogen.
I'm just trying to picture what a fractional update looks like inside a cell. I mean, they aren't doing calculus in there.
No, obviously not. They are responding to biochemical gradients. A cell releases a specific concentration of a protein.
Okay.
The neighboring cells detect that local concentration, and then they adjust their own protein expression to match it. It is literally a chemical local information exchange. Through this unforced dynamical system, billions of independent cells basically average out their chemical states until the entire tissue reaches an agreement on a certain biological function.
So it's the exact same math as the banquet hall,
Right.
just executed with proteins instead of vocal cords.
Exactly.
The source scales this up dramatically, though, from the microscopic to the macroscopic. It points to large-scale energy systems, specifically power grids.
Oh, yeah. A power grid is arguably one of the most complex, multi-agent systems humans have ever built.
Really?
Think about it. You have thousands of generators, solar farms, and substations, and they're all feeding into a single massive network. To prevent a catastrophic blackout, the entire grid must maintain a perfectly stable frequency. In North America, that's typically 60 hertz.
So if, say, a massive coal plant in Ohio suddenly drops off the grid,
Right.
the frequency would destabilize, right?
Instantly.
So how does a wind turbine in Texas know to adjust its output to compensate if there's no central computer fast enough to command every single node simultaneously?
Well, the grid itself acts as the interconnection topology. The generators literally feel the physical, mechanical resistance on their own turbines.
Wait, they feel it physically?
Yes. If the frequency drops across the grid, the physical resistance changes locally at the turbine. The sensors on that specific turbine run the consensus protocol. They calculate the difference, and they adjust their output.
That's incredible.
They are only reacting to the local physical state of the wire they are physically connected to. But because every node is doing it simultaneously, the massive grid balances its own frequency organically.
So the network is the computer. That makes total sense for things bolted to the ground, but the text brings in kinetic movement too. It mentions the coordinated control of autonomous vehicle fleets, like autonomous drones on land, in the air, and in space.
Right. If we connect this to the bigger picture, think about a constellation of hundreds of satellites in low Earth orbit, or maybe a swarm of military drones.
My immediate thought is, why not just use a massive supercomputer on the ground to fly them all? Like a video game player just controlling a fleet.
You'd run into two major issues there: latency and fragility.
Latency meaning delay.
Yeah. If you are flying a swarm of drones at high speeds, the speed of light communication delay between a ground server and the drains is just too slow. By the time the central computer calculates that two drones are going to hit each other and sends the command to dodge,
They've already crashed.
exactly, they're already wreckage. Furthermore, a central computer is a single point of failure. If that central server goes down for any reason, The entire swarm falls out of the sky.
Right, which is obviously terrible. So instead, you program the drones to only care about the drones immediately around them.
Precisely. You give them a localized interconnection topology. A drone only pings, let's say, the 4 drones within 50 feet of it. It shares its altitude, heading, and speed. It runs the consensus protocol that fractional update averages its trajectory with its neighbors and adjusts.
But hold on. If I am a heavy physical drone moving at like 200 miles an hour, I have momentum, right? If I just rigidly average my position with the drone next to me and slam on my thrusters to match it, the physical inertia might cause me to overcorrect, swing too hard, and crash into a totally different drone.
That's a very real problem.
Because agreeing on a number on a spreadsheet is one thing, but physical flight seems infinitely more complicated.
Which is exactly why consensus dynamics is just one subset of a much broader mathematical field called cooperative control.
Cooperative control.
Consensus is merely agreeing on a state or a quantity. Cooperative control is translating that agreement into complex physical coordinated action while actually obeying the laws of physics.
Because the source does list several sibling sciences under this cooperative control umbrella. It mentions the rendezvous problem, synchronization, and flocking and formation control.
Right. Let's break those down. The rendezvous problem asks how independent agents, starting from unknown locations, can agree on a single geographical point to meet using only local information.
Like trying to find your friends in a crowded theme park without cell service.
Perfect analogy. Then there's synchronization, which is about aligning in time, making sure actions happen at the exact same millisecond. But flocking and formation control, that addresses your exact concern about momentum and inertia.
Right, like birds maintaining a V formation. How do they account for the physics of it?
The text specifically cites something called Lagrange networks when discussing moving leaders and fully distributed flocking.
Lagrange networks.
Yeah. A Lagrange network isn't just a data network, it is a system governed by Lagrangian mechanics. This means the mathematical model actually accounts for kinetic energy, potential energy, and inertia.
Okay, so the drone isn't just a dot on a graph to the algorithm. An algorithm actually knows the drone has mass.
Exactly. The consensus protocol is modified to respect the physical constraints of the agent. When the drone calculates the fractional update to match its neighbor's speed, the algorithm factors in the energy required to make that move and the momentum the drone already possesses. It smooths the whole transition. This is what allows an entire swarm to follow a moving leader fluidly, expanding and contracting around obstacles without breaking formation or colliding.
But I'm kind of stuck on the processing power required for that. If you have 50 drones constantly running complex physics equations based on the movements of all their neighbors, wouldn't the sheer number of possible flight paths just fry their onboard processors?
It absolutely would if they were trying to solve the entire puzzle at once. To prevent that computational overload, artificial intelligence and computer science utilize a method briefly noted in the source citations called distributed constraint reasoning.
Distributed constraint reasoning. Can you break down how that actually limits the options an AI has to choose from?
Sure. Imagine you are trying to schedule a meeting with 50 really busy people.
A nightmare.
Right. If you try to look at every possible combination of everyone's free time, the search space is infinitely large. You would never figure it out. Distributed constraint reasoning aggressively prunes that search space locally.
So a drone doesn't calculate every possible direction it could fly?
Exactly. It only calculates the moves that satisfy its immediate constraints. If the protocol dictates a drone must stay at least 10 feet away from its neighbor, the AI instantly crosses out any flight path that results in a distance of 9 feet.
It just completely ignores those possibilities.
It doesn't even do the math for them. By only reasoning through the strict, localized constraints, the AI radically reduces the amount of math it has to do. It passes its reduced list of acceptable flight paths to its neighbor, the neighbor does the exact same thing, and the network rapidly locks into a global formation without freezing the processor.
So systems theory, graph theory, Lagrangian physics, and computer science constraint algorithms. They all interlock to solve the exact same problem of getting multiple units to act as one.
That's the beauty of it.
And the transition the source material makes next is fascinating because it takes all of this pristine logical math we've been talking about and drops it directly into the absolute messiest system on the planet.
Human interaction.
Yep. The source states that these exact consensus models are utilized in social and philosophical domains to analyze how groups reach agreement through deliberation and debate. I mean, we are literally mapping graph theory onto a boardroom argument.
It is an incredibly rich field of study, actually. Humans engaged in a debate are fundamentally multi-agent systems.
Right.
We have initial conditions, our pre-existing biases and opinions. We interact over specific interconnection topology, who we trust, who we actually speak to, and who has social influence over us.
And our local information exchange is just the literal exchange of words and arguments.
Exactly. What's fascinating here is the work of Gregor Betz and his research on debate dynamics, which is highlighted in the text. Betz utilizes these mathematical frameworks to run literal simulations on human debates to see how opinions shift and whether a consensus can ever actually be reached.
So what does this all mean for us as human decision makers? Like, how do you mathematically simulate a town hall meeting about a new park, for example?
Right.
You can't just average human opinions like a thermostat.
Well, you represent the debate as a graph. You have individual nodes representing the people, and you have nodes representing the arguments themselves.
Oh, the arguments get their own nodes.
Yes, and the simulation evaluates specific mechanics of deliberation. For instance, the source mentions simulating the exact moment a brand new argument is introduced into an ongoing debate.
So like someone drops a new piece of evidence on the table,
Yeah.
like a brand new environmental study about the park. How does the math handle that?
The new argument is assigned a truth value.
Truth value. What gives an argument a high mathematical weight in a simulation like this?
It basically represents the logical soundness and the evidentiary backing of the claim. If the new environmental study is highly verified and universally understood, it enters the network with a very high truth value. The simulation then just watches the ripple effect.
Because that high truth value node
Yeah.
is now connected to the human nodes.
Right. The people exposed to that argument run a cognitive version of the consensus protocol. They evaluate the difference between their current opinion and the truth value of the new argument. If the truth value is heavy enough, their internal state updates. Basically, they change their mind.
And because of the interconnection topology, they then turn to their neighbors, the people who trust them, and pass that updated state along.
Exactly. The mathematical simulation physically shows the cascade of changing minds moving through the network. Betz's work investigates under what conditions that single new truth value can force the entire group to shift its consensus to a totally new outcome.
You know, applying systems theory to human arguments completely changes how you view a difficult conversation. Like, if you were preparing for a contentious community meeting, it's really easy to feel like your single voice just gets lost in the noise. But looking through the lens of consensus dynamics, you don't need to be the central node with a megaphone.
No, you are an agent injecting a localized truth value into the system.
Because it's an unforced dynamical system, compromise and averaging are essentially inevitable. If you introduce a highly reasoned argument, a heavy truth value, into your specific local connections, the math dictates that the network must account for it.
Right.
Your initial condition mathematically alters the trajectory of the group's final agreement simply through the ripple effect of the interconnection topology.
It kind of removes the emotion from the debate and reduces it to structural mechanics, doesn't it? Every single node plays a mathematical role in the final state of the system, whether that system is a network of genes, a swarm of drones, or just a society of humans.
Exactly. We started today with a theoretical room of shouting people and uncovered the unforced dynamical systems that govern our reality. We saw how the exact same mathematical demand for compromise, that consensus protocol, balances the mechanical resistance of our power grids. It allows artificial intelligence to prune search spaces to fly drones in formation, and it even maps the cascading ripple effects of human opinions.
This raises an important question, though, because the through line here is that local rules dictate global realities. The final outcome is never arbitrary. It is rigidly bound by the initial conditions of the agents and the specific shape of how they are connected.
And I want to leave you with a final thought to mull over based on that.
Yeah.
We've learned today that in unforced dynamical systems, reaching a final agreement relies entirely on the interconnection topology, who is connected to whom. If autonomous machines and biological cells can so reliably reach a stable consensus using these protocols, it forces a hard look at our own networks. When our human groups completely fail to reach an agreement, when our meetings break down and our society violently polarizes, is it because our arguments truly lack truth value? Or is it simply because the interconnection topology of our social networks, who we are actually connected to and who we utterly refuse to listen to, is fundamentally broken? Thank you for joining us on this deep dive. Keep questioning your local rules of interaction.